So hello everyone. So welcome to the second lecture of this PYQ Solution series, in which we are going to cover next 10 questions from quantum mechanics. So let's start the first question. So in this question, a beam of 4 kilo electron volts electron from a source is incident on a target which is 50 centimeter away. Find the radius of the electron beam spot due to Heisenberg's uncertainty principle. So, first question for our learning purpose is that why there could be electron beam spot. So, the simple reason is that there would be uncertainty in its transverse direction too, and hence spread will happen. And this is exactly same kind of problem which you study while studying double slit experiment, double slit experiment using the particle, that is electron. So we are required to find the radius of that very electron beam spot, and we need to use the Heisenberg's uncertainty principle. So the uncertainty principle formulated by Werner Heisenberg states that position and momentum of a particle cannot be simultaneously determined with arbitrary precision. For an electron beam, this beam limits how tightly the beam can be focused, leading to minimum spot size on the target. And this is where we need to find the radius. And additionally, it could be interpreted as a beam of electrons which is moving along a specified direction, and it encounters a diaphragm with slit, and for that reason electrons undergo diffraction. So this is great example of wave particle duality, WPD. So we have been given the energy of electron, which is 4 kilo electron volt. When converted to joule, it is 6.408 multiplied by 10 to the power minus 16 joule, and the distance to the target is 0.50 meter. So first we are required to check whether it is relativistic case or not. So we are going to check if non-relativistic approximation is valid, and if it is not valid, we will be moving to relativistic case. So what is the difference? The difference is very simple, that energy gained in the non-relativistic case is P square upon 2m simply. What kind of energy it gained? It is kinetic energy. But if that is not a non-relativistic case, that means it is a relativistic case, then we are going to use the formula E square equals to momentum square C square plus rest mass energy square. But in this case, as the ratio of velocity of this particular system, this particular electron in the system, and the speed of light is around 0.3, and it is good for non-relativistic approximation. Okay, so we are going to use the energy, which is P square upon 2m, and from that we could get the value of momentum, expression of momentum, that is under root 2me. When we substitute all the required constants, we will be getting momentum to be 3.42 multiplied by 10 to the power minus 23 kilogram meter per second. And once we get the momentum, then we know that the uncertainty in momentum is of around same order. For that case, we will plug that and we could get the uncertainty in position as well. But for the time being, we have written that in its expression form only and not in the calculated form. So if the initial beam has an uncertainty in transverse position, because we know that this transverse position is creating a spread, that means we are required to find the radius. So then by the uncertainty principle, it must have a corresponding uncertainty in its transverse momentum as well, and that is given by this particular expression. And we are using the same form of expression, that delta x times delta px, that is uncertainty in position, multiplied by uncertainty in momentum in the same direction, is greater than or equal to h bar upon 2. So this transverse momentum uncertainty causes the beam to spread as it travels, and this spread could also be uh, represented by this particular theta. Because suppose that from here electron is traveling, and this is the slit it encounters, and this is the screen. So it will go that, and then it will spread. Okay, and this would be the maxima, central maximum, then minima. So this is the minimum spread or electron. This is the minimum spread or electron which we are going to calculate. So this is momentum in transverse direction. This is the momentum in this particular direction. So we know that this is theta. So we will be using the trigonometry to get to that particular value. What kind of trigonometry? That sine theta is equal to, and we know that when theta is very small, we simply use the approximation. Sine theta is approximately equal to theta. So, and this line is very important that I request you all to write this particular line in the introduction part itself. So as the beam travels the distance L, the radius of the spot will become larger and larger because it is spreading out. So we could write that spread at L distance away because of this theta angular spread, the distance at the screen, that is a spread or radius at the screen, will be simply the initial spread. Initial spread is given with this. This is x naught, delta x naught. This initial spread plus the extra addition. So extra addition is this. This is extra addition because the electron traveled with angular spread of theta by distance L, and this is the initial spread. Okay. So now we are going to perform some mathematical manipulation. So to minimize the spot size, okay, we need to have this spot size only. So minimize the spot size as we want to ascertain the spot to be definite, or you might think the radius from the center to its first minima of the diffraction pattern we are observing here. This is the diffraction pattern what we are observing. Okay. So to write this particular line is very important. That is why I have marked it in another form as well. So we differentiate the whole radius which we are going to find on the screen itself with respect to delta x naught, and for that to be minima we set it equal to 0 provided that the double differentiation for that minima is greater than 0. Double differentiation. So this is what we are required to write as well. So this conditions finally provides you the opportunity to have that particular expression to be minima. Okay. So when you solve this, you will get the optimal beam width given by delta x naught equals to under root length multiplied by h bar divided by 2p. So when we substitute or plug in this value here, okay, we will get the R minimum. And that R minimum, when we calculate, it will be twice L h bar upon p whole under root this particular value. So when we now you have L to be half meter, h is reduced Planck constant, and this momentum we have already found. So when you substitute all the values, you get 1.8 micrometer. Therefore, the minimum radius is this much, and this is what we are writing the conclusion. So the minimum radius of the electron beam spot on the target due to the Heisenberg's uncertainty principle, because there is a spread in the transverse direction as well. A spread in transverse direction. So electronic beam will spread, not spread, but uncertainty. The correct word is uncertainty. So electron will spread, and this is what we were required to calculate, that is radius. So that spread is approximately 1.8 micrometer. This fundamental quantum mechanical limit demonstrates why electron microscope and other high precision electron beam instruments faced ultimate resolution limit, that you cannot resolute more than that, and that is around half angstrom, which is determined by the uncertainty principle. Now, the next question, we are going to estimate the de Broglie wavelength of the electron orbiting in first excited state of the hydrogen atom. This is pretty simple question. We are not going into the introduction part because you will cover it yourself. So the first, the general equation for the energy of the electron in the hydrogen atom is given by minus 13.6 electron volt upon n square. This n is nothing but principal quantum number. So for the first excited state, this n is going to be 2. For the first excited state, n is going to be 2. So whenever you put the value, you will finally get that it is minus 3.4 electron volt. So we all know that kinetic energy is negative of the total energy. Kinetic energy is always negative of the total energy in such a model of hydrogen atom, and it is precisely Bohr model of hydrogen atom. So you get kinetic energy to be 3.4 electron volt, and once you get the kinetic energy, you will get the momentum as well by using this expression, and momentum is 5.447 multiplied by 10 to the power minus 19 joule. And once you get the this is not momentum, this is kinetic energy being converted into joule. So this is the kinetic energy, and when you plug this particular value in the momentum's expression, you will get the value of the momentum, which is 9.96 multiplied by 10 to the power minus 25 kilogram per meter second. So once you get the momentum, you would easily get the de Broglie wavelength, which is h upon momentum. So de Broglie wavelength is 0.665 nanometer. Now let's jump to the conclusion. So the de Broglie wavelength of electron in the first excited state of the hydrogen atom is approximately 0.665 nanometer. This wavelength reflects the wave-particle duality of the electron, emphasizing the quantum mechanical nature. Such insights are crucial for understanding the phenomena at atomic scale, including electron diffraction and formation of the atomic spectra. And this whole atomic spectra leads to the diverse field of study known as spectroscopy. Spectroscopy, and about it you will read in the next part, that is molecular physics. Now let's move to the next question, that is question 13. So we are here just required to show that mass and linear momentum of a quantum mechanical particle can be given by m equals to h upon lambda b and p is equal to h upon lambda respectively, where h, lambda and b are Planck's constant, wavelength and velocity of the particle respectively, and we are to comment on the wave particle duality from these relations. This is simple question from 2019. This is pure theoretical question. I think I need not to describe it much. So here we are going to write the introduction, that you introduce the de Broglie hypothesis. You introduce what does it really prove, that is wave particle duality, and then you just you need to show it. Okay, so from the hypothesis you could directly jump into the mathematical model. Okay, so for momentum, we could write that as per the de Broglie, h is equal to lambda is equal to h by p. So how did we get that for the photon? If we treat a photon to be some, suppose a kind of particle, so what we could write, E equals to p square c square, e square equal to p square plus c square plus rest mass energy square. So for photon, this rest mass energy square is 0, and we simply get E equal to pc, or p equal to e by c, or p equal to h by lambda. Okay, so this is how we derive it, and we know that p equals to mv, so you can simply write mv equals to h upon lambda, and then m is equal to h upon lambda v. Okay, then we are required to make the most important part of this solution, which is comment in wave particle duality, because this is what we understand, and this is what might help us to express our knowledge, so that our examiner will be impressed to give us the maximum marks. So the derived relations, that is m equal to h m is equal to h upon lambda v and p is equal to h upon lambda underscore the wave particle duality of matter, they reveal that properties traditionally associated with particles, that is mass and momentum, can be described using wave particle characteristic. Wave characteristic is simply that if something has a description related to wavelength, then we could say that that is the wave characteristic of that particular form of matter, radiation, whatever we are going to use. So this duality is fundamental in quantum mechanics, and it explains the phenomena such as electron diffraction and quantization of atomic orbits. And how do you know that atomic orbits are quantized? Because we observe atomic spectra, which is not continuous, which is not continuous but discrete. So that is the main observation which helps us to conclude that there is quantization of atomic orbit. So here we have the conclusion that expression for mass and momentum could be uh, derived from the de Broglie wavelength, highlights the intrinsic connection between wave and particle in quantum mechanics. This wave particle duality is crucial for understanding various quantum phenomena and has practical applications in fields like electron microscopy and semiconductor technology. That's it. Now state and express mathematically the three uncertainty principle of Heisenberg, highlight the physical significance of these principles in the development of the quantum mechanics. It is again the question from 2019. So this is pretty simple theoretical question. So we are going to introduce it in the simple yet effective manner that Heisenberg uncertainty principle is fundamental concept in quantum mechanics formulated by Werner Heisenberg 1927. You could reduce the word here by using your own expertise, summarization expertise. It states that certain pairs of physical properties known as conjugate pairs cannot both be known to arbitrary precision simultaneously. This is the most accurate definition. Most accurate definition. Always use it. Most accurate description. Okay. And mathematically, using the operator or commutator algebra, you could describe that commutator of this conjugate pairs is non-zero. Because it is non-zero, so you cannot measure those quantities with infinite accuracy at the same moment simultaneously. So we know that Heisenberg's uncertainty principle can always be explicitly expressed in three different forms. That is, first form is position and momentum, second form is energy and time, and third form is angular position and angular momentum. So here we know that delta x times delta p, where delta represents the uncertainty in the measurement of the position and momentum, is always greater than or equal to h bar by 2, and the commutator for the position x cap and momentum p cap is iota h bar. As it is not zero, it implies that position and momentum cannot be simultaneously determined with arbitrary precision. The same goes correct for the energy and time, and the same goes correct for the angular displacement or angular position and angular momentum. That is, the non-zero commutator is the main villain here, which is stopping you from measuring the position, momentum, energy, time, and angular position, angular momentum same time simultaneously with infinite precision or arbitrary precision. Now, physical significance is the most important because these all are ratified concept, but physical significance depends on your understanding of these concepts. So the first thing that comes as a result of this Heisenberg's uncertainty principle is limits of measurement. You cannot limit the position and momentum simultaneously with arbitrary position. Then it also proves the wave particle duality because this principle highlights the wave particle duality, emphasizing that these all things depends on each other. Okay, and they also depend on the measurement context, as we have solved the PYQs in this lecture earlier. Okay, so I think this is the result of that particular This is the result of from that particular concept. Okay, question 11. And then we could get to understand the quantum behavior that at very smaller level, okay, the things are not as observable as we observe them at larger level. Okay, so at larger level, there could be well-defined position and well-defined momentum at the same instant, but at the smaller level, at the quantum level, that is not true. And then in the advanced field of physics, you could understand the quantum fluctuation based on such theories. Okay, that states of energy states fluctuate very rapidly, and that is one of the main villain in development of quantum computers. So taming the Heisenberg uncertainty principle to its greatest possibility could help us to achieve the cornerstone of the physics in the quantum world. Now let us solve with the next question. For a free quantum mechanical particle under influence of one-dimensional potential so that energy is quantized in the discrete fashion, how do these energy value differ from those of a linear harmonic oscillator? Okay, so we are going to have one-dimensional potential, and within that one-dimensional potential, we are going to prove that energy is quantized in discrete fashion. Discrete means it is not continuous. Like energy could have a value of only 10, 20, 30, and so on. It could not be anything in between that, for example. So introduction goes as follow that quantum mechanics reveals that particles can only occupy certain discrete energy level, which is known as quantization. Like we know that angular momentum is always quantized. So this angular momentum could have the definite value, that is h bar, 2h bar, 3h bar, and so on. But if you say that it is going to be 1.5 h bar, then this is wrong. This is not quantized. So it could be anything in between. It could be h bar, 2h bar, 3h bar, but it could not be anything in between the milestones h bar, 2h bar, 3h bar, so on. So this concept was first developed in the early 20th century by scientists like Planck, Bohr, and Schrodinger. Just remember these names, and these names will give you the better marks because your introduction would be better. Introduction would be better. So to show the quantization of energy, consider a particle in one-dimensional potential well, which is described by this potential function. That potential is zero inside the well, but as soon as you go in the boundary, it is going to be infinite. And we know that such a system is well described with the time-independent Schrodinger equation. Okay, so time-independent Schrodinger equation's most general formula is this, which you should always remember that it is del square psi plus 2m upon h square multiplied by e minus v psi equals to 0. So inside the well, we know that v equals to 0. So this particular equation takes this form where d square psi divided by dx square equals to 2me upon h square and multiplied by psi x equals to 0. So now what we do, we will put this particular value as k square. So this will help us to solve this differential equation easily. So when we solve that, the solution of this particular kind of differential equation is of sinusoidal form. So we are going to write that solution is a sin kx plus b cos kx. Now we have the solution. So what we will next, what will we do in the next? So we'll simply apply the boundary condition because we know that for the well-defined wave function, the boundary condition should be always true. And what kind of boundary condition? That whenever the potential shoots to infinity, the wave function should cease to exist at that particular position. That means at boundary, the wave function should be 0. Whenever x is going to be 0, the psi x is going to be 0 as well. Okay. So at x equals to 0, we know that this is going to be 0. So a sine 0 plus b cos 0 equals to, which gives us b equal to 0. Okay. This is implies that sign. Okay. So from the boundary condition at x equal to 0, we got to know that, okay, our constant b is equal to 0. Our constant b is 0. So now we will, because we have two boundaries, this is the potential well, this is infinity, this is infinity, this is equal x equals to 0, this is x equals to L. So we have computed psi x here, okay, and we got that b equals to 0. Now we will do the same part here as well when x is equal to 0, because that is also a boundary. We have two boundaries, okay. So we know that a cannot be 0 because b is already 0. If a is going to be 0 as well, then there would be no wave function. So a must exist. So we know that this is going to be true, that if a cannot be 0, a cannot be 0, then this has to be 0 at the boundary. So from here we could find the value of constants within the k. That if sine some angle is 0, then that angle is of the form n pi. Okay, and look here, n comes, that leads to the quantization, because because we know that sine function is periodic function, so it will repeat each and every definite interval. So because it is repeating, so there will be some kind of quantization leading being led by this particular equation, that kl is equal to n times pi, because this will only lead to sine kl equals to 0 at the boundary. So we know that k is equal to n pi upon l. So by using this particular information, we are going to write the energy levels, which is h bar square k square upon 2m. That will lead you to this particular expression, that energy is equal to n square pi square h bar square upon 2m l square, where n is equal to 1, 2, 3, and so on. Okay. And look, we have used this particular form of k, which we have assumed here in this case, and this is what led us to this energy form. So this is simple class 10th level mathematical manipulation. Now we have the energy given for the harmonic oscillator, linear harmonic oscillator, which is n plus half whole in bracket multiplied by h bar omega. So we need to compare this to this energy and this energy, and we need to write the key differences. So energy levels for the particle in a potential level are proportional to n square, while for the harmonic oscillator they are proportional to not the square of n but just n plus half. So we know that the spacing in the first case, that in the case of the potential well, is going to be increasing in order. Okay, so spacing between energy levels in potential well increases with n, because we know that it is directly proportional to n square. But for the harmonic oscillator, it is directly proportional to n plus half. So it is not going to increase, but that is, it is going to be constant only. And there is no 0 point energy in the case of one-dimensional infinite well, but that is not true with the case of harmonic oscillator, because in harmonic oscillator, even when n is going to be 0, you are still going to get energy as h bar omega by 2. This is what we call 0 point energy. And this is again one of the characteristic of quantum mechanics or quantum physics. Okay, and then you are required to conclude the answer that quantization of energy is, in the one-dimensional potential well demonstrates how boundary condition leads to discrete energy level. This is what we are asked to prove, and meeting the demand of the question must be shown in conclusion. Okay. So examiner will get to know that, okay, understood the question very well, because introduction and conclusion helps examiner to gauge your real talent of writing good answer. And again, the basic thing, that this concept is foundational in the quantum mechanics. It affects the phenomena like electronic configuration in atom, or the behavior of the particle in the confined system or spaces. And the comparison with linear harmonic oscillator highlights the diversity in the quantum systems itself. Okay, so there is no such like unique quantization for each and every potential system. Now we are going to use the uncertainty principle to estimate the ground state energy of the harmonic oscillator. We have done this previous time that at first you are required to write the energy equation. From the energy you will find its minimum. Okay, and once you find the minimum you will get some results. You will use those results to get your final answer. So introduction goes as follow that in the uncertainty principle, again the same introduction we are not going to repeat. So what we will do, this is the statement, mathematical statement of the Heisenberg's uncertainty principle, and this is how we have written the energy. So energy is nothing but the sum, it is a sum of kinetic energy plus potential energy. So first term of the right hand side is kinetic energy, second term is potential energy. And when you write the energy, you are going to substitute the value of momentum always from the statement of Heisenberg's uncertainty principle. So we get the complete energy equation in the form of delta x only. Form of delta x only, that is position only. Delta x is nothing but position. So now you have this particular form of energy which you must minimize. So when you minimize it, you set the differentiation of that energy with respect to delta x to be 0, and provided that the double differentiation is always going to be greater than 0, that its double differentiation is always going to be greater than 0. So we need to write that statement for the correctness of this question, provided that provided that is going to be 0 for minima. This is the condition which always holds true. We have read it right from class 11th and 12th. Okay, and this particular equation when you will solve, you will get that delta x whole square is h bar upon 2 m omega. Now when you plug this particular value of delta x in energy equation, you get the energy equation to be h bar omega upon 2. This is what we had just 0 point energy, that is ground state energy. 0 point energy, which is ground state energy for the harmonic oscillator. Now again the same conclusion which you are going to write. Now let's move forward in the next question, that a blue lamp emits the light of the mean wavelength 4500 angstrom, that is 10 to the power minus 10 meter. The rating for the lamp is 150 watt and its 8% of the energy appears as light. So how many photon emitted per second by the lamp? Okay. So now this is the introduction that photon emission from the light sources can be quantified using the energy wavelength relationship for the photons, that is E is equal to h nu. Okay. And this line, I think it is not required here to write that much unnecessarily. So just I have strike it off. So don't write it here. So solution goes that you need to convert this 4500 angstrom in meter, which is 4.5 multiplied by 10 to the power minus 7 meter, and the energy Hc upon lambda. So you could get the energy value of the energy, which is going to be 4.14 multiplied by 10 to the power minus 19 joule. Okay, and we have the power 150 watt, and only 8% of that power is being utilized by the lamp. So you are going to multiply 0.08 multiplied by 150, that is 12 watt, and in 1 second, okay, we need to calculate that only for the 1 second. So for 1 second it is going to be 12 joule only. Okay, so total number is total power in 1 second by the energy required. So power required in 1 second or energy required in 1 second is 12 joule, and this is the energy uh, of the one particular single photon. So when you divide, you get the number, which is huge, 2.717 10 to the power 19. Okay, so this much photon in 1 second would be emitted. Simple. Now we are going to consider a Hermitian operator A with the property A cube equals to 1, so that A is equal to 1. This is the question from 2020. You could solve it in various way, but I think this question is solved in very much simple manner here, and this question was, I think it was worth 15 marks. So I'm going to solve it in some other lecture where we will expand this solution because this solution doesn't seem appropriate worth 15 marks. Okay. So let's move forward. We will cover it in the next lecture. Find the uncertainty in the momentum of a particle when its position is determined within 0.02 centimeter. Also find the uncertainty in velocity of an electron and alpha particle respectively. Okay, so if they are going to ask the uncertainty in velocity, then you are smart enough to understand that you first need to calculate uncertainty in momentum, because momentum will only lead you to the quantity velocity. Okay, and when they are located within 15 multiplied by 10 to the power minus 8 centimeter. So again, you are going to write the same introduction in your own language. Obviously, don't copy paste it, just improvise it. And the uncertainty principle is given by delta x delta p greater than h bar by 2. We know it pretty well. Write it in the term of the momentum, then find the momentum by substituting the value, because you have the delta x given here in the question itself directly, that it has to be determined within 0.02 centimeter. So this is what we have taken the delta x. Okay, so this is the momentum. Now you have momentum, so there is another case. You need to find the uncertainty in velocity for electron and for alpha particle both, but this time the uncertainty in the position is of this particular order, that is 15 multiplied by 10 to the power minus 10 centimeter, or yes, meter. In centimeter it is 10 to the power minus 8. So what you are going to do, you have the momentum already here, you just utilize that value to find the uncertainty in the velocity. Okay, and you have all the these all things you have already calculated earlier as well. Okay, so we are again taking the momentum form, that is momentum is greater than or equal to h bar by 1 2 delta x. You have this delta x this time equal to 15 multiplied by 10 to the power minus 10 meter. So we have wrote that particular value, and this momentum could be written as delta VE times ME. So ME comes into division side in right hand side, and when you divide that, you get 3.86 multiplied by 10 to the power 4 meter per second for electron. And for alpha particle, the mass has to be different, and that is why the velocity has to be different as well. And then you conclude the whole thing in the conclusion, and this question is solved as well. Now we have the last question of this lecture, that a particle of rest mass m0 has a kinetic energy k, that's and then we are required to show that its de Broglie wavelength is given by lambda equals to hc divided by under root under its k bracket starts and within bracket k plus 2 m naught c square. So this is what we are required to show, and once you show that, we are required to calculate the wavelength of an electron of kinetic energy 2 million electron volt. So what will be the value of lambda if k is very less than m naught c square? So this m naught c square is nothing but the rest mass energy, and if kinetic energy is very less than rest mass energy, we know that it is non-relativistic case. I am telling you just for the sake of knowledge here. So you are going to introduce the de Broglie wavelength and those all thing, and then move to the solution part. We know that total energy of the particle is given by kinetic energy plus rest mass energy in the quantum world. And in the case of relativistic physics, how do you know that it is relativistic? Because we have this particular value of kinetic energy for electron, which is going to be 2 million electron volt. So given kinetic energy is greater than rest mass energy of electron, which is around 0.511 million electron volt, and this is 2 million electron volt. So we are going to stay with the relativistic version. So we know that two versions of two expressions for energy, 1 and 2, and from these two, when we combine them and when we perform the mathematical manipulation, that is, we substitute the value of E from first equation to second equation, by simple mathematical manipulation, we could write that momentum is of this particular form. Okay, this is simple mathematical manipulation, nothing else. Do it yourself. And once you know the momentum, you could know de Broglie wavelength as well. And once you know the de Broglie wavelength, you could establish the relationship which they asked in the question itself. That is, lambda equals to hc divided by under root starts within kinetic energy multiplied by bracket starts and kinetic energy plus twice of rest mass energy. Okay, so this is what we have proved just now, and once we have proved, we are required to find the wavelength of an electron with kinetic energy 2 million electron volt. So you are just required to plug in this value here, and you know all the values for the electron already, that rest mass energy and this all thing. So once you solve it, so we are going to solve it very easily. Like, let me do it here manually. Hc um, is I think it is around 1240 electron volt nanometer. Okay, and this is 2 million electron volt. Then bracket starts 2 million electron volt plus twice of rest mass energy of electron, that is twice of 0.511 million electron volt. This is what you are required to solve. Use the calculator, you will get the answer pretty fast. Okay, so this is what I think you will get. 1.597 multiplied by 10 to the power minus 13 meters. So calculation is your own expertise. Do it the way you want to do. Okay, but I believe use the ready-made notations that will help you to write the solutions very effectively with minimal mathematical manipulation, and that will save your time, that will make your copy look better and more arranged. And now we have the condition given in the question, that what will be the value of lambda if kinetic energy is less than m naught c square and very very less than m naught c square. So whenever we do that, if k is less than m naught c square, then we can neglect this particular value, and this will be the ultimate result of that particular expression. So in this equation, we are going to just neglect this value, and we could finally write that it is simply hc divided by root under k m naught c square and 2 k m naught c square, and when you do some manipulation, you finally get h upon 2m kinetic energy under in the under root itself. Okay, so this is the classical relationship. So whenever there is kinetic energy which is very very less than rest mass energy, then we get the classical approximation, and we are going to use the formula which is classical in nature, that is E is equal to P square upon 2m, and it is not a, it is actually kinetic energy. Okay, so the conclusion goes as follow. The derived expression for the de Broglie wavelength is this, what they have asked in the question. Okay, and for an electron, we have got the value of wavelength when the energy of electron is 2 million electron volt, and within this approximation the wavelength simplifies to this value. It highlights the classical limit of the de Broglie wavelength, and this is what we have in the conclusion part. So I think we have done great in this lecture. We have understood a lot of concept to its core. We have minimized the calculation part, and we maximized the physics argument upon which our whole examination depends. So let's meet in the next lecture. Thank you and bye till now.